People sometimes wonder if you can fill a space with circles. But circles don't have the kind of nice property of tiles that they lay side by side and fill all space. If you put a bunch of circles together in a region, you find that there are spaces in between them. But if you think a little bit, you can put smaller circles in the spaces between the bigger ones. It turns out it is possible to do this with smaller and smaller circles ad infinitum, such a way that the given region is space filling in the limit of an infinite number of circles. You can get 90% fill or 99% fill, and if you're really, really patient, I suppose 99.9% fill, and this is what it looks like. If we are going to fill our space with circles, we need a rule that will tell us how to make these circles smaller and smaller. And this is what we have. This is commonly known as the area rule. This is the area of the ith circle. This A without a subscript is the area of the region to be filled. And we see that in the numerator here, we have 1 over n plus I to the c, with c and n being the parameters of this process, which can be chosen by the people making the pattern. Down in the denominator here, we have a sum, 1 over n to the c, 1 over n plus 1 to the c, n plus 2 to the c, all the way to infinity in the style of calculus. It is natural to ask, does this converge? Can I get a number out of that? It actually has a name. It is called the Hurwitz-Zeta function and is well known in mathematics. You can also see that if we add all the a sub i's together, we get a sum of all of these terms, and every one of these terms appears down in this sum. So if we do that sum of all of the possible circle areas, we find that the total of them is just a, because we get the same here as here when we do the sum. We have an area rule which tells us the sizes of the circles that we want to put into our filled region. We also must have a rule for how we put them in a way that they never overlap each other. And for this, we have a flow chart that shows how this is done. We have the beginning here, the 0th circle, and we choose a random location for it. We then test to see whether it overlaps the boundary or any other circle. If it does not, we put it into our database and say it is a placement. It's been placed and we have a place for it. We increment I, come around here and go on to the next circle. And again, we have to make a choice, and if it overlaps, we go and choose another random location. And this is how we actually do the placement of the circles. You might wonder whether this occasion sometimes stops, comes to a halt. Actually, for some parameters of c and n, there's a formal mathematical proof in a mathematical journal that there is no halting. It never comes to a stop and is therefore space filling. We will now look at an example of this with only a few circles placed. This is what it looks like. You can see that we've got a small number of circles here, and they're getting steadily smaller. No two of them are the same size. So this is a nice way of presenting how the circles go together. But there is another way that we can do this, which we'll see next. This is the very same scene, except that we have now put red bands around all the circles and also around the outer perimeter. The width of these bands is the radius of the next to be placed circle. So all of the red area consists of places where no circle can go, but there are some black areas where there's no interference with the red bands, and the little black areas represent all of the places where the next circle can go. It would appear here that the most likely place would be here or here, but depending on the random choice, here, here, or here, could be the next place that the circle comes in. So we are going to, in a short time, see some movies of this. And you will see the red and the black, and the circles in that case are in white. So we will move on to that. We've seen the movie for c equals 1.1. This is covered by the formal proof of known holdings, so it goes on indefinitely. We will now look at the movie for c equals 1.2. We saw the movie for c equals 1.2. It is believed that this is also a case where there's no holding, but there is as yet no proof of that. We will next look at the case of c equals 1.3. One 1.3, as you observed, does give us a good bit faster filling. The probability of halting is about 1% here, so it does halt, but very rarely. The last movie was for c equals 1.4, and we can see that this gets pretty tricky. The halting probability here is about 0.3, and many of the runs do in fact end with halting. We will now look at a final example where c equals 1.45. At this c value, most of the runs halt, and I had to go on for quite some time to find one that persists this way. You'll see the black area is very tiny, and you can easily imagine that it would halt. we have talked about the area rule as an area rule. It is called just an area rule because it goes far beyond just the areas of circles. It turns out you can use a huge variety of shapes, and as long as you follow the area rule and the placement algorithm, you can make space-filling images. This shows a few examples here. This is circles in a square. This is annular rings, and these are squares that all have different orientations. This is trapezoids. This is kind of almost look like hot peppers. This is the character and these are the numbers from 0 to 9. Butterflies are my favorite here, and there's other ways to do them. I've mentioned that it may take a lot of trials to make placements, and there are some interesting systematic trends in that with this random algorithm. And here we see how it goes. This is a log plot. It's the logarithm of number of placements along here. We go up to 1,000. 10 to the 3 is 1,000 in this logarithmic scale. In the vertical we have going all the way from 1 up to 10 million. And here we have the steady increase in the number of trials, the cumulative number of trials for c equals 1.1, 1.2, 1.3, and 1.4. You notice that the number of trials needed here increases rapidly as you go to a higher c value. These are all for n equals 1. Here, for c equals 1.4, we find that we need about 7 million trials to place 1,000 circles. An interesting fact about this, which is completely unexplained, is the fact that on a log-log plot like this, the slope of this curve is the exponent of a positive power law. This one has a positive power law exponent right about 1.1, right about 1.2 here, right about 1.3 here, right about 1.4 here. So we see that this has the same exponents to a good approximation that we use as a negative exponent in our trials in our area rule, but it's a positive exponent for the number of trials needed. This is completely unexplained, and nobody has an explanation for this, even a hand-waving one. At this time, there's only one book on this subject. It was published only a couple of years ago. It has lots of colorful pictures in it. The first 6 chapters are merely descriptive with lots of color illustrations, to the point that one person called it a mathematical coffee table book. The serious mathematics comes in the last 4 chapters, including some material on how you can create your own patterns of this kind. So it is available where books are sold. As an example of what can be done, there was a lot of sort of applied mathematics needed to create this space-filling set of monarchs. This actually won a prize in the art show associated with a mathematics meeting. And this shows the kind of quite variable things that you can create with this algorithm.